welcome to the last day of the conference. So, my name is Chaitanya. I'm a new faculty member here, and I'm chairing this session. It gives me great pleasure to introduce Pedram Roushan, who's going to be leading this tutorial. And he will teach us about quantum dynamics with qubits.
Thank you. Well, wait to the end. Well, maybe. Well, it's a great pleasure to be here. I like to thank the organizers for providing me this very privileged opportunity to present some of our works in here. Let me see. Yeah, so well, I get to it. It's a tutorial, so hopefully. I think, sorry. This year marks the 100th anniversary of matrix mechanics, and many of us have been talking and presenting and discussing and celebrating this 100-year anniversary. But also, it's time to also reflect back in our field of quantum simulation, which is about 4 decades old. So. In early 1980s, Richard Feynman, among others, figured out that there are many or certain problems in simulating quantum systems that are very hard for classical computers, or so-called Turing machines. And then Feynman, we always remember Feynman because he had a very memorable way of saying things. This last sentence that you have seen many, many times. I'm not going to read it for you. Because of that, we remain it as Feynman contribution, but in fact was Feynman among others. Well, if I put it in a modern language, he was saying that there are many body problems that we need to have built quantum processors. So 40 years ago, he was dreaming about all these processors that we have. So we are very fortunate that we are actually living to see and live up to his dreams, and something that he was discussing 4 decades ago is now become realities that we can talk, and we'll be enjoying playing with them every day. In particular, I want to focus today on an announcement that Google made in December 2024, which is introducing a new platform called Iwill. Probably Julian talked about it too, but I want to tell you how this processor enabled us to do quantum simulations besides error correction ideas. So we all get the feeling that, things has changed and we are really starting a new time, but I want to be more specific and give you something that to show you what happens under the hood of these recent progress. Particularly, we should look at the gate performance, and I'm showing you performance of a Sycamore processor, which is the older processor compared to Willow. So I want to tell you that the effort of my colleagues at Google for about 5 years or so was able to shift every curve that you see to its left. So you're seeing a histogram of errors for single qubit, 2 qubit, and readout, and you can see everything has shifted. So it takes lots of energy to move things to the left, but that's what you get at the end. But this, in turn, opened doors to many new experiments, such as those that I will be talking about you today. In particular, I want to talk about an experiment maybe related or in the spirit of high energy physics, another experiment in the spirit of related to condensed matter quantum simulation, and something recently that we posted on arXiv, which is kind of opening the door to our really practical quantum advantage that we all have been thinking and been discussing it. So if an organizer getting angry at me, is it really a tutorial? Well, if you put it in quotation and then tilt it, maybe it is. So I checked with our chairman, and he's saying if it's understandable for everybody, then it's tutorial. I don't know what other categories of talks out there, but anyways, I'll try to make everything understandable with some knowledge of physics at the graduate level. So that's the claim, and then that should be qualified as a tutorial. But these are the 3 works I like to talk about. So I'm an experimentalist by training. I think there was good coverage of superconducting qubits the other day, but I just say it so you don't ask me tough questions at the end. So we are working with Josephson junctions. They are made of aluminum, and there is an aluminum oxide that are separating these two aluminum islands. And they together, when you shunt it with a big capacitor, they form a nonlinear elements. And the physics of this element has been discussed, I'm sure, during the conference. But what we do in here, this is the last picture I can show you from our devices before we go to 2D and put them on top of each other, or rather fabricated in 2 layers. And also, this is done at UCSB. At the time, I was a postdoc, so I can show it to you how these things look like. You have a Josephson junction, which is a little hard to see in here, and then a capacitor connecting to it, and an adjustable coupler, which goes between every 2 qubits. So you can imagine that you can go 2D with this architecture, and then every qubit, you have to figure out to have a readout for it. And then, every qubit can be read at the same time, meaning that we can read the entire quantum state by many, many shots, maybe about 100 kilohertz rate. You can repeat your algorithm and read quantum states of the system. So together they form a very gigantic atom that we can control the degrees of freedom very, very, very precisely by having wires that are kind of coming and engineered into this platform. If that was too much fabrication and whatnot, we have a Hamiltonian. At the end of the day, when you put the pieces together, this Bose-Hubbard is a very good describing the model very precisely to a good degree. But what we are going to do, we are going to have a time-dependent parameters in here, and we are going to move them to create gates, and we are not going to focusing on the native evolution under this Hamiltonian, which we could have done it. So let me get to the first work, which is about is a lattice gauge model and a study of a lattice gauge model and string breaking and confinement in this model, and was published recently. Gauge theories have been one of the cornerstones of our physics and our understanding for elementary particle interactions, as well as also appears in condensed matter settings. Here I'm having a very simple gauge theory written, putting in a lattice, which involves of matter qubits and gauge qubits. And so there is a term which couples matter field coupling, mediates the interaction between matter qubits. And then there are 2 terms to consider for the energy stored in electric field and energy stored in the magnetic field. And there is a mass term which tells you, or the charge term. So these are all qubits. They're not distinct from each other by design. I'm just trying to give them tags and names to realize this model that is written in here. Some of the terms in this, well, okay, maybe not yet. This constitutes a gauge theory because there is a local degree of freedom that every term in this Hamiltonian, you can go and verify for yourself, commutes with it. So for every term you see in here, there is a local operator that commutes with it. But we can actually take advantage of this local degree of local symmetry of the model, and we can factor out the qubits degrees, the matter degrees of qubits in this sense. So arrive at the new Hamiltonian, which does not have the taus in it anymore, and it only have cap x and y and z. And in this model, where the matter fields have been integrated out, you can sense the presence of a charge or magnetic flux through these AV and BP terms. Basically, if there is a charge or a magnetic charge or magnetic flux going through a site, through this plaquette, it would be catched by these BP terms. And if there is an electric charge, it would be catched through the AV terms. So this is a bit probably familiar to you now. This is the Kitaev model, but then now we have these extra terms that we have to take care of. I see. The first step in studying this model is to come up with an ansatz to arrive at the ground state of the model. It's not very, it doesn't have any closed form solution in contrast to the case of the Kitaev model. When HE and lambda are equals to 0, you could actually have a closed form solution to synthesize the ground state of this model. But generally, when these two parameters are non-zero, well, you need a scheme, and the scheme, the ansatz we used in here is by parameterizing these first single qubit operations, theta, and figuring out numerically the optimal value of this theta, which gives you the highest overlap with the wave function of the system obtained numerically. So at this moment, we are using classical computers to figure out how to arrive at a very effective gate sequence to arrive at the ground state of the model. Nothing, is not only quantum computers, but also a heavily usage of classical simulation at this point. But here we are showing that we can measure the local observables for this Hamiltonian, and we are trying to show with this energy plot that, in fact, for every choices of alpha and a non-zero choice of h of e, we have a very good overlap with the ground state of the model. The phase diagram of this model, that is the starting point, actually goes back to many decades ago by the work of Fratkin and Senker. So some of us were not even born at the time, some were in diapers. But what it is that it's known what the ground state of this model is going to do. So that's not actually the exciting thing to do. It's many years old. But what is exciting to do is to study the dynamic of elementary excitation in this model. And that is very quickly falls outside the capability of classical computers to do it for you. The phase diagram tells you that when HE and lambda are small, we would be in a topologically deconfined phase. And then when both of them are 0, you arrive at this point, which is the Kitaev point, the Kitaev model. And then when the electric field becomes strong, or the coupling matter and gauge coupling, the matter gauge, the interaction between matter mediated through gauge becomes strong, then you enter a confined phase. So the prediction would be that in the deconfined phase, the motion of the particles are independent from each other. And then when you enter the confined phase, then the motion would be confined, and there would be as if there is an elastic string which is connecting them. And we're going to try to visualize this elastic string. Nevertheless, this is a very challenging problem for us to do. There's lots of gate it takes, and I just want to flash you the numbers so you can see this is really the state of the art in quantum simulation with superconducting qubits, in a sense that it takes many runs of the experiment to allow for error mitigation and whatnot, as well as the number of gates and whatnot. So the next thing is to create a Trotter evolution of the Hamiltonian. I showed you we have the ground state. Now we are going to create a Trotter evolution of this model, and we are going to watch the dynamic of the excitation. The first thing, of course, comes to mind is to create a pair of excitations, and that's very simply done by applying an X gate in here. And then what we can see in here is that as a function of time, as we evolve this system forward with this Trotter evolution I just mentioned, you can see that when lambda equals to 0, the two excitations starts next to each other. But when you come back in later instances and ask where are the excitations, it seems they have gone all over the place, and the probability of finding them in any place is more or less equal to each other. But when lambda equals to 2, and this is large values of lambda or large value of HE, you can see that wherever we left them originally, more or less they stay the same. So it's an indication of the confinement that exists as a change of these parameters. I see big unsatisfaction in your eyes, so you want to see maybe a stronger indication of confinement. So what you could do is that you can create a little more fancier initial states. What I'm showing you here is that we are trying to think about it in this way. We are giving it some initial angular momentum to initial state. Well, the precise initial states that we are creating are these two, sigma psi plus and psi minus, but you can think about them, and only intuitively and not precisely, is that there are two bodies that are spinning or rotating around each other with some nonlinear angular momentum. And as if like an Earth and Moon going around each other, and imagine that if the gravitational field comes to a stop, they're going to fly apart from each other. So this non-zero angular momentum analogy, or rather initial states, allows us to see much better clear signatures of confinement. Basically, in one case, when lambda equals to 2, in the confined case, you can see that the separation of them, as we measure later, is not going to change as a function of time. The other case, you can see they're just flying apart from each other. I mean, it's a small place. They don't have very far to go, and they eventually get saturated to some value. But you can see that when lambda equals to 0, they get really, really far from each other rather quickly. So these are the signatures of confinement, and I want to show you another cut, essentially, through the same data. This data showing more or less the same thing. When there's a 22% chance that we find one particle in here, and in those cases, this is where the other particle is. There is 16% chance to find one particle here, and the other color shows where is the other particle. And you can see when lambda equals to 2, there is always a very sharp high color particle find. So meaning that when you find them, their separation is not changing and is well defined. Okay. So these are the signatures of confinement, but I told you that in QED, the confinement of quarks and whatnot is explained by a string flux that is connecting the particle. And now we have the luxury of quantum simulators, so we can measure and we can visualize these strings that is connecting them, and then we're going to see when we're breaking it. This is the observable associated with the string. And what we are going to do is create a pair of particles and stretch them, taking to the boundaries of the small group of qubits that we have, and kind of fix them there. And therefore, according to the model, there would be a string connecting them. And we are going to watch and take pictures by measuring this observable after every cycle, what's happening to this string. So you can see that in the case of the confinement, for instance, the string is clearly visible in forming in here, as I was showing where it was a stretch originally. And as a function of time, is more or less stays the same. Then you lower the value of h, and you're going more to all the confined case. Now you see a string starts to wobble. And when you go all the way down to h equals to 0.1, that is where the strings that is it's more or less very even hard to define. But nevertheless, you can change the evolution of it. So as you know, whenever experimentalists show you a color plot, you should not trust them. So I show you a cut through the same data, so you can see for yourself that the same story is repeated in here, and I'm not hiding anything here with these colors, which we could. That's what about the strings. Now we can talk about the string breaking. This elastic string, when you stretch it enough, the tension in it goes very high, and then eventually it prefers to break. And when it breaks, two new excitations are formed out of vacuum, and this is the mechanism we like to study in here. Of course, the vacuum fluctuation could lead to spontaneous creating of particles at the same time, so we need to subtract these from each other to see that in fact, when we have a string, we are enhancing the probability of finding new particles by this mechanism. So what you would do, you would subtract some background vacuum where you don't do this scenario. So the scenario is that, again, you stretch the string, you create a pair of excitation, and then you move them. So essentially, at time equals to 0, you create this configuration. And then you come and measure where if there are new excitation has been created into this model. And you can see, indeed, for values of lambda, lambda of 0.5 in this case, you can see the probability of finding strings is far more enhanced in the top part where probability of finding excitations, particles, have been enhanced substantially on the top part where there was originally a string stretched across. So for instance, you can come again, I'm showing you a cut because colors cannot be trusted. You can see that, for instance, for this A1, this is this location, the probability of finding excitation there is substantially different than finding A2, which is lower there, and it goes where the background is, I guess, and this shaded line shows you where the background is. Okay, is that good? So, yeah, it's also, this was recently published back-to-back with the work with the team, Quora team. So with this, I think we are showing the state of the art on what can be done with these lattice gauge models, which has been written, I don't know, a few decades ago, but the dynamic in them remained really needed to be explored, and then we are getting to the limit that is really challenging for classical computers to do certain simulations. So the next story I want to tell you is a story related to condensed matter system and a story of localization in the absence of disorder. The story is as follows. When you're having a crystal like a metal and whatnot, there is no, in the absence of any scattering center or disorder, the wave functions are extended and they have a block wave function, and the conduction would be perfect and everything is glorious. But then as you start to introduce disorder in the system, as was done in this, the work of Phil Anderson, in the absence of diffusion in certain lattice models, he showed that if the disorder passes certain threshold value, then the wave function become localized around some centers, and then they change in nature and become exponentially localized, essentially. For a while, the physics folklore was that this is okay, and this would not happen in interacting systems, and the interacting systems would be always delocalized and would be showing conduction. This worldview shattered in 2006 by the work of Basco, Aligner, and Altshuler, which they showed that, in fact, even you can get localization even in many-body system, even in interacting systems. Now we ask this question, and we are not the first one who are asking this question. This question has been asked since 1980s, many mechanisms, different mechanisms, and many papers. We are asking, since their disorder is part of both of these scenarios, can we see this localization in the absence of disorder? And I want to show you one scenario, and I want to tell you the advantage of doing such a thing with quantum processors. So first, let me show you how does it look like. It's there, and then we understand. I'm going to explain to you where it's coming from. Consider a Hamiltonian which is translationally invariant, meaning that all these parameters are outside the summation. There is, for reasons become clear in a minute, I call them actually matter and gauge qubits again. But don't worry, that's just a name. So there is matter qubits, and then there is gauge qubits, and then there is sigma x acting on matter qubits, and then there is this three-body term which mediates again the interaction between the matter sites, and then there is a x term which you can call it the electric field and whatnot. So the point is that this Hamiltonian is there is no disorder in it. And when you come up with this gauge sequence associated with it, again, you can check that this is translational invariant, C naughts and single qubit rotation. This pattern has no disorder in it, okay? Then I consider two initial states. I want to tell you those are also disorder-free. The matter qubits are put on sigma x or sigma z, so it's the same everywhere in this ring. And then the gauge qubits, the other qubits, are put in some tilted angle. The angle doesn't matter, except one at the center, which has a different angle with respect to each other. So is a product state. Every gauge qubit is pointing to some point in the Bloch sphere, except one of them, which is pointing the opposite, because we want to see if this energy imbalance that we created, is it going to be diffusive, or is it going to be, or we're going to see the absence of diffusion for this case. So in this translational invariant unitary and this translational initial states, when we run the experiments, we see some totally strikingly different behavior. In one case, we see that the excitation, wherever we put them, is going to stay the same place as a function of cycles and on the gauge qubits. So the first color plot is gauge polarization, okay, is this green term in the Hamiltonian. The second term is this last term, and these two right panels are the sum of the alt energy terms together. But also you see that in this case, the excitation propagates and leads to these ripples that we can see as if there is no localization in this case. Where is it coming from? How did we manage to synthesize such a thing? To understand this, let me show you how one could kind of hide disorder in a model. So this is a group of qubits on a link of a 2D grid to the lattice, and this Hamiltonian has disorder in it, has a binary disorder in it. Has these z terms on every edge, and then has the x term, and has this four-body term, xxxx, associated with every j value. And these g's are now inside the summation. They are binary disorder. The way that you could hide this disorder and arrive at a translationally invariant Hamiltonian is as if you have extra qubits, you can introduce them, and with these ancilla qubits, you can introduce an observable operator associated with this degree of freedom. And then you can see that this operator is going to be a constant of motion, is not going to move. But now you arrive at a Hamiltonian, which is disorder-free, and all the disorder could be encoded in this degree of freedom, which is constant of motion. Let me walk you through what I have mean. So maybe I say the connection with the lattice gauge model. What we are realizing is a lattice gauge model. Again, there is a local degree of symmetry. And now these choices of the initial values of sigmas, it would lead to a gauge sector, and we are going to have a decoupled gauge sector, because whatever you choose for sigmas is not going to change during the evolution of the system. And then you can create, for instance, if you choose all these sigma x to be +1, you are in a disorder-free gauge sector. If sigmas x's are chosen randomly, you would be on a disorder sector. And if you choose sigma z's to be +1, then you would be at the superposition of all sectors. So these choices of sigma x, this way of introducing this observable, essentially brought the Hilbert space, because of this symmetry of it that you're introducing. It broke the Hilbert space into decoupled sectors. And now with initial state, you can choose to be in one sector or the other, or the superposition of all. So now let's go resolve the mystery. In this case, the top case, yes, sigma x was +1. I was in a disorder-free sector. And in the lower case, we are in the superposition of all disordered sectors. And the dynamic is simultaneous dynamic in the superposition state. Okay? But the benefit of having quantum processors is that, again, you can go to much larger systems and dimensions that are accessible to classical computations. Tensor networks are the really way to go for simulating this physics. But then they would be suffering when you're trying to snake a tensor on on a 2D structure, but for us, it's not very difficult. Maybe it is. I didn't do it, so I don't know how difficult for a student to go to 2D structure and study the same physics. Again, it's a color plot, and you should ask for cuts through it, and these are the cuts through the same data I'm showing you. In this case, we are putting an excitation on the gauge qubit on top left in here, and we are, again, creating two initial states, which are translationally invariant. They are disorder-free, and we see very two distinct behavior in these 2D cases. In one case, you can see there's a very free motion of this excitation coming and exchanging with the other qubits, and here you have a hard time even to seeing the red color to stay on this place. On the other case, you can see it's more or less a state on where it was placed originally and very slowly coming in, and the data, of course, is somewhat affected by the decoherence. Okay, let me see. So why we are doing all this physics that we are doing? Well, let me explain this data, and then I would highlight that what's advantageous to doing this way of studying many-body localization. There's actually a very genuine advantage for this approach. You might say, well, you know, we could do many-body localization in our system because entanglement grows logarithmically, so classical computer can probably handle it, but there's actually differences that is worth considering. Let's measure the entanglement entropies, and yet another parameter which is very rather straightforward for us to measure, and we consider three scenarios. One is that we are in a disorder-free single sector uniform. There you go. So I think it's a disorder-free sector. You can measure the second order Rene entropy, or you can consider 100 disorder realization. You go to a gauge sector, which is disorder. You keep choosing these sigma x values to be on different sectors. You repeat the experiment 100 times, and you average over disorders. Or you can measure entropy by starting in a superposition initial states, which, as I said, is the superposition of all gauge sectors. And at cycle 8, I can make a cut for you to go through, at size 8, system size 8. This was done on a ring or maybe open chain of 1D open chain of 18 qubits. What you could see is that indeed in a disorder-free sector, entropy is going above of the case that you have disorder. So this is the traditional MBL 100 disorder systems, and this is the disorder-free. But what is a little strange is that this superposition is having more entanglement entropy, growth of entanglement entropy, than the other two. The answer is that what we have done in here, maybe without paying too much attention, is that there is a configurational entropy which enters this thing. So when you think about the density matrix that you have, there would be a configurational entropy entering the density matrix in this case. And when things become nonlinear in density matrix, trace of rho squared is the first thing that got nonlinear. Both these terms matter, and that's what we are seeing in here. So we are measuring the dynamical entropy between qubits as a result of the dynamic, and we're also seeing the configuration because we are dealing with evolution in many, many sectors at the same time. This can be leveraged to create an algorithm, which we have not implemented, but is actually quite interesting, that now actually you can really sample disorders much faster than what you would do in polynomially faster in what you would do in contrast to what you would do in the regular sampling that you could do in your classical computer. The superposition state actually exists, right? So you're really in superposition of all disorder sectors. And that can be actually manifested in this Grover search scheme and phase estimation to figure out that, what would be a local observable that you're interested in the case of MBL. In the traditional case, you evolve the system and then you measure it and you have to repeat it, and the accuracy that you get is accuracy epsilon if you want. It scales this way, the number of samples needed scales this way. But here you can in the spirit of Grover search, you can come up with an algorithm. I mean, it's not a new algorithm. I'm just saying it's a Grover search to figure out how to do this problem with much less overhead. Okay. Yeah, let me start the last thing and hopefully biting a few minutes into the question and answer. The last story I want to tell you is the story of measuring out-of-order time correlations. And maybe you're familiar, maybe not. Maybe I walk you through the distance. Maybe I just explain this picture. You could think about them as the quantum equivalent of the butterfly effect, classical butterfly effect, and I show you why they're coming along. This work is a recent archive submission, and I think it's pointing us the way toward genuine practical quantum advantage. One of the biggest or very commonly encountered problems in quantum dynamics is measuring few-point correlation, two-point correlation, or correlations in time or space between points. Essentially, you want to know if you move and change a parameter in a system, how the other points are affected. When you want to write down a Hamiltonian for a system, you want to know how many terms to write and from what point you can truncate safely. Or you have a molecule, let's say, and you don't know the strength of these bonds and whatnot. You have even a spectrum problem. You want to know what is the role, what would they play in the spectrum of the problem. Even that problem, the Hamiltonian can be described that you can create an evolution under that Hamiltonian, and you can measure and try to understand the contribution of that unknown. So essentially, very, very schematically, you can think about that the changes associated with this unknown in your Hamiltonian can come and lead to a different evolution, and then you can, by tuning this, you can hopefully figure this out. But the story is not as simple as this. Usually, there would be ergodic behaviors and scrambling of the quantum information that makes this problem not as easy as it is. Maybe I give you similar in the spirit related analogy from classical physics. When we want to understand the correlation between 2 points, what we would do is that we create a perturbation in an initial state, could be a flip of the wing of a butterfly in Brazil, and we look if it results in a tornado in Texas or not. Right? And this has been successful in terms of the Lyapunov exponent and understanding classical physics. So why can't we just start from there? You know, create a dynamic where you change the initial condition or something in the Hamiltonian and see what happens. Unfortunately, this is not going to work out because let's say you have two initial states that are tiny different from each other, and when you evolve under the same evolution, same Hamiltonian, you arrive at two final states, which is the overlap of them is preserved under the unitary evolution. So they are not going to diverge from each other in their Hilbert space, and the overlap would be the same. So these simple ideas that we are familiar with from classical physics is not going to work out. And also these kind of ideas that are just direct time-ordered evolutions also rather very difficult. So what people have said that could be done is spin echoing in the spirit of a spin echoing. You have to undo the evolution and hoping that you mostly cancel the undesired parts, and then you are left with some effect of interest that you're interested in. And I want to show that is actually quite effective way of encoding and trying to understand information, try to create sensitive in the ergodic systems. Okay, if this butterfly was absent, U and U dagger would cancel each other, you get nothing. So you can say butterfly creates a little perturbation, and then most of the undesired evolution would be canceled out, and I can end up with the desired effect. So OTOC or C2 is defined this way, and the OTOC squared, which is again a more and more bouncing, moving forward and backward in time twice, is defined this way. And there is a very nice interference. Well, you can write it down, and if you're an equation type of person, you should be happy. But if you're not like me, you would just try to look for an intuition picture associated with these very long strings of operators. And I want to give you this interference. I don't know, you want to call it whatever interference pattern you like. I forgot the name. But anyway, it's just interpretation of this equation. Here we are in OTOC squared, we are having two loops going, and you're coming back, and you say if I'm coming back or not. And here you can think about bouncing off B as mirrors and M and coming back to where it started. So this ideas and whatnot is not, again, by us. It's been studied and has been discussed by many, many people, particularly in understanding ergodic dynamic in black holes and chaos and thermalization from some that are really at the edge of chaotic behavior. This allows you to kind of slow down to your favor. Well, if it's not super clear, I want to show off my skills of using Gemini, and this is what I've been saying is that in a crowded room, and the spirit of tutorial, I should say this, in the crowded room, this OTOC allows us to focus on a desired conversation where you want to kind of spy on someone or something. That's all I have been saying. So let's look at some evidence of the data. So we are going to choose U to be a random quantum circuit which have some gates, is almost ISWAP, ISWAP, but it's called ISWAP-like, is a ISWAP and a CZ gate, or C-phase gate, I think. And then there would be random choices of single qubit rotations, maybe square root of X, a square root of Y, and somewhere in between. So there's a finite set of random qubit gates, non-Cliffords, that you can choose from. And this is OTOC measured as a function of cycles. Initially at early cycles, this value is 1, meaning that the perturbation from the butterfly has not reached to the measurement point. But at some point it reaches, and you can see it's affecting where the measurement points are. The thick lines is the average value over many random circuits, and the instances of random circuits are shown in the background. But you see large fluctuations, meaning that every circuit, which are distinct from each other by the choice of random gates, leave its own distinct signatures from other ones because they are very different from the mean value. And that's what we would like to take advantage to encode our problem of interest. Let me be more precise in here and show you that I told you that the goal is to slow down dynamics and ergodic dynamic before the quantum information gets scrambled quickly. And this is the evidence for it. So here I'm showing you OTOC squared over a grid of 90 qubits or something, I forgot. And you can see how this front of OTOC is propagating in this average behavior. And you can see its fluctuation and how the fluctuation propagates. So you run many, many instances, maybe 100 instances of circuits or so. And this is the fluctuations that you see associated with this. And particularly, you notice the fluctuation is associated where the front of the OTOC is. And here again are the cuts through this data, essentially for some choices of qubits. And you can see that time order correlation, C1, where there is no butterfly, where there is no echoing, decays rapidly. But then the out of time ordered one decays much slowly. I get to this magenta later. The other two, you can see OTOC and OTOC squared. Decay much slowly. In fact, we're claiming they decay polynomially. And therefore, I want to claim that we have managed to kind of slow down this ergodic thing. And the next step is to now encode a desired thing in this Hamiltonian. Let me show you an experiment, and we're going to come back to it. This is to maybe convince you that this interference picture I was mentioning is actually a very intuitive thing, but we're going to read a little deeper into this physics. What we are going to do, we are going to inject a certain number of, we are going to average over choices of these random circuits, essentially. So we are going to insert a group of single qubit rotations, and then we are going to do another group for these third and fourth operations. And we are going to now change these choices, and we are going to average over. This is equivalent to a phase shifter in this interferometer that you see. But what is interesting, and I like to highlight, is that you see that what we could do, we can control the value of OTOC as is shown by these correlation values. So by orders of magnitude, particularly OTOC squared. I think this tag is backward, sorry. That's why everything looks backward. Yeah, so basically what I'm trying to show that this is highly sensitive to where you insert these things, and then you can see that the value of OTOC can change order of magnitude of where you are. Confused over these things. But to understand this data, I have to tell you that the true language to understand these out-of-time order correlations is in the Heisenberg picture, where the state, quantum state, is frozen and fixed, and the operators are spreading and evolving in time. Basically, an operator, this is a 2D grid of qubit, let's say. The operator is confined to a few qubits, and then as the time evolves, goes up, then the operator spreads and then become non-commuting with the measurement site. Or more precisely, there are two things that happen. When you have a Clifford circuit, the operator is just going to spread. You know, one sheet of operators turns into another 2D sheet of operators, and so on and so forth. But when you have non-Clifford circuits, in addition to spreading, there would be an entanglement. And that is the essence of what makes this problem computationally very difficult, meaning that after several layers, you have many Pauli strings that you have to take care of. So here I'm showing pictorially here. You start from, in the Pauli state space, you start from something which is simple, and then it evolves, you have many of them that you have to, at any given cycle, that you have to take care of. And that is the essence of the computational challenge. I'll get back to you in a second. I don't know why I showed this again. So now in the spirit of this, we can understand the difference between OTOC and OTOC squared, and we can understand where there would be non-contribution signals and where this is coming from. Because when you're trying to do the computation, you always want to figure out which Pauli strings are inconsequential and drop them. And you don't want to keep track of all of them, right? You have to kind of just be very effective in which one you're tracing and you're following. When you're dealing with the OTOC, what's happening is that these Paulis, they are branching out, but then there are instances that they are coming back together. And this is where the major, when they come back together, then you have to, they would be leading to a sizable signal, and that's where you need to keep track of them to understand what's happening during the evolution. But for OTOC squared, there is much more complicated story. There would be this contribution to it, but there would be very non-intuitive relation between these Pauli strings, which would lead to a constructive signal, which you can interpret this as a formation of large loop constructive interference. It's just interpretation. But if the four Pauli operators follow this algebraic relation, they would also contribute to the sizable signal. Therefore, a priori, you don't know which one to drop, because if they manage to satisfy this relation, then you got to be sure that you have to keep track of them. As a result of it, we can see that our Monte Carlo simulation schemes fail to chase them when we are generating such scenarios. You see, for C2, for OTOC, the experiment and exact simulation for a small size and Monte Carlo very much following each other. But when you go to C4, particularly the terms that enjoy the contribution from such a thing, such relations, you can see that the Monte Carlo start to not being able to capture it, and of course the exact diagonalization simulation is not be able to help you when you go to much bigger systems. So here is the catch. You go to a large system of 65 qubits, and then you measure this term. Well, because it was very sensitive to this Pauli insertion, so you can measure OTOC, and you can measure these two contribution terms separate from each other, because if you remember, there was a huge dip there. And then we can go and construct a model, an empirical error model, which tells you how well we are doing. This is signal-to-noise ratio. But note that we cannot put a last point in here because this is beyond the classical computation. But all I can tell you that if there was a point, according to our model, would have been in this range, has sizable signals. So how long it takes to actually put a point in here, this is the estimate on the tensor network contraction physics if you want to do it. And I forgot, this is 3 years or something. I forgot the exact number. So of course, you can optimize your tensor network. That comes at a cost. But the time of the simulation, nevertheless, does not come below a year or so, 3 years or so. I forgot the numbers. In the spirit of conclusion, I want to say that this experiment and outperforming classical computer in this experiment is very distinct from the experiment you're familiar with probably from 2019. When we are sampling a bit string, which was the essence of the quantum supremacy experiment 2019, yes, we are saying that the quantum computer can sample bit string from output of a distribution of a random quantum circuit very effectively, which is the case in here. We can measure observable. But the distinction comes that when you sample a bit string, if you had another quantum computer, there would no way of verifying that you got it correctly. You can sample and sample as much you want. There are hundred millions of billions of bit strings. So there's no way a bit string is going to repeat itself if you do millions of measurements. But if I say that the value of OTOC is 0.35 or something, then this can be verified with another classical quantum or classical computer, well, quantum computer in this case. Therefore, it can turn into a decision-making problem. And I was told that this belongs to a whole different chapter of classical complexity problems. This is in BQP, which is part of QMA. I don't know what I'm talking. But you can see the distinction. And the local observable can be used as a decision problem because it can be verified by another quantum, but that was not the case for the bit strings. So I want to claim that this is a very solid step forward towards quantum advantage, practical quantum advantage, because the nature of these problems are very distinct from each other. Maybe I should not, maybe I should stop. And what I want to show you that, in fact, this was the spirit of conclusion, that, in fact, I was telling you that we can imagine we have a physical system. We didn't go to an actual physical system yet, but we can say that, hey, look, there is an unknown in our evolution, and we can identify that unknown. In this case, of course, we just put with hand. You can define a cost function, and then you can verify, and in this case was just verification to figuring out what the value of that unknown is. So basically, this can be encoded in this spirit. I should maybe leave some room for questions. This was the work of Google large Google collaboration, but most of the work's actually done by students that we borrow from various institutes for extended period of 1 year in the program called Quantum Residency Program. And lots of details I didn't get a chance to talk, but my colleague and friend Zlatko would be covering hopefully some of it for me. Thank you.
Okay, so we started a little late, so we have time for questions.
Thanks, that was really nice. I was wondering, in lattice gauge theory simulations, there's a very natural connection between the lattice and error correction.
Yes, yes.
Where like the expectation values are just
yes, violation of the, yes, yeah.
I was wondering, do you leverage that in some way? And like, does that allow you to maybe embed error correction in the
yes, 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 yeah. Well, maybe actually on the other work, which was the disorder-free localization, it's the same. Actually, it was even the same Hamiltonian. Yes, if you are meant to be in a sector, you can measure you call it syndromes in the case of error correction. You can measure them and you can post-select on them. So some of the data, which was meant to come from a given sector, at the end of the evolution, you could verify that you're in a sector or discard it if you move. But the ones that, let's say, come from all the sectors, you could not use it. But on the lattice gauge particularly, I said we're going to use this local gauge symmetry, and we kind of integrate it out. So there was not that luxury anymore. There was two Hamiltonians I wrote. First had the lattice gauge, then I took advantage of it. So it was slightly different at the end, yeah.
Oh, yeah, very nice. I have a question that's all with the pedestrian. I apologize for asking this, but which of these quantum simulations, if any, cannot be simulated on a classical digital computer?
The only claim I made, it was this very single point in here. The rest, if you really have put energy into it, it takes about a few days or less or something. That can be simulated.
Yeah, that's true. But more interestingly, I guess, is as you develop these models, it stimulates quantum theorists to come up with explanations of the results, which is very nice. I mean, new insights into condensed matter physics and many physics. At some point, though, we reach a point where the quantum simulations are putting out results that we cannot understand ever by any kind of theory.
Yeah.
It's just the way the world is.
We are not there yet.
Not there yet. That would be a very interesting point. Thank you.
Sure. Well, you have to really work hard, and sometimes people come. But I think what has happened so far is that we came up with things that we didn't expect them. After we explained them, theorists says, oh, the scars, where's Misha? The scars is a very big example. I mean, it was in very 10 qubit, 15 qubits. But then after he published that, people say, oh, of course, let me explain it for you. So, yeah. Okay, anyways.
Yeah, thank you for that interesting work. I wanted to ask about, like, I didn't quite understand the limitation that comes into the simulation from the quantum processor itself. So maybe if you can also give a comment on, I mean, if you have the same quantum processor and you can enhance the single gate and the two single qubit and 2 qubit gates, or you can scale up your processor and add more qubits, which one would help those simulations more in this way?
Okay. I think coherence helps more. So this is why I showed this. Trust me,